Hello everyone, I'm Isabella. I'm really excited to be here tonight to talk to you about diabetes, machine learning and core ML. I'm a robotics engineer and I have diabetes and I've been living with it since I was a child. And I'm making hundreds of decisions a day to keep myself alive. Now, I have been dreaming of offloading this decision making to a machine for years. Back when I was studying at the ETH in Zurich, these machine learning algorithms were already around, but the technology to run them wasn't. And thankfully, in the meantime, we have started to all walk around with these powerful computers in our pocket, and even this model. And with it, we started to wear sensors that measure so much about what's going on in our body and around us. And so this is, of course, the ideal technology platform to help me and millions of other people to help with diabetes self-management. And 3 years ago, I founded Ayuda Heuristics, my own company, to essentially do exactly that. Now, tonight, I'm going to talk to you a little bit about diabetes, and then I hope you can take away two things. First of all, I would like you to kind of have some idea what sort of problem you could be solving with machine learning. And second of all, I also would like you to kind of know how to get started and how to use core ML to do just that. Now, let me talk a little bit more about diabetes. So, diabetes is a disease no one understands. So no doctor can tell me how much insulin to take for what I eat, or for how active I am, or for how stressed I am, or for whatever else is going on in my body. And like millions of other people, I'm using trial and error to essentially try out what to do. And along the way, I'm developing my own rules of thumbs to essentially my heuristics to kind of manage this whole thing. This is, of course, a huge psychological and a cognitive burden. And what we do at Ayuda Heuristics is to take that burden, to learn that burden from the user and put it into an app and have the app take care of that. We're starting out simple. So in the initial phase, the app would really learn things about what you do. So for example, hey Isabella, you're going to give a talk at Apple. You may be a little bit stressed out, take 2 units of insulin now. And eventually it would grow more sophisticated and essentially just tell me, take 2 units of insulin. Of course, the more sophisticated version is a far better user experience. But, you know, taking insulin, you could take too much or too little, and it's dangerous. And so we have to make sure when we're at that stage that we know it's 2 units. So now I'm going to zoom out a little bit out of diabetes. For those of you who probably know machine learning, you can see how this is an ideal case for machine learning to approach this problem. Machine learning is a growing collection of literally hundreds of algorithms. And they're all similar in a way that you, as the developer of these algorithms, you don't have to specify or find the exact solution of your algorithm. You essentially let the algorithm learn what the right solution is. And you do that by presenting it with loads of data. Now, you can see how diabetes is one of these problems, but I would like you to kind of like have a problem in mind that's maybe a little bit easier to visualize. So if I can just ask you to shout out, how many colors do you see on this picture? And what are the colors you see? Blue and cream, black, silver. So it's actually really white. It's actually really amazing. Us humans are unbelievably intelligent, right? We are able to look at the picture, and then we are able to kind of like ignore that little shade that you have in the top of that blue and say, like, that's not white on that blue, that's just blue, and it's just a reflection of the camera. And we're actually even able to see, like, oh, there's some shade in this picture, that's also just a reflection, so I can ignore that, don't have to call this color out. But if you were to think about that, you would have to write an algorithm that is calling out these colors that you've just called out. It actually would become quite tricksy. Essentially, if you were to go with the RGB meter over this image and were to just see what you see in the RGB meter, you can actually see there is like literally thousands of different shades of blue and thousands of different shades of white in this picture. So like a seemingly simple problem, like how many colors are in this picture and what are those colors, essentially for a computer, it's really tricky to come up with an exact algorithm that would be able to tell us that. And so that's exactly the sort of problem that machine learning can help us with. So now, how would you go about with that? You kind of like, you have now an understanding maybe what machine learning could solve for you, but how would you go about with solving that? And I generally split the machine learning solution into 3 different steps. So there is kind of the first step is you have to select an algorithm. I told you there's hundreds of algorithms, select one. You have to then train that algorithm. And then once you have that trained algorithm, you're kind of ready to use it in your production environment to essentially run. You can see like many talks generally tell you like, don't worry about the selection and the training. It's quite a complex subject. And just use a trained model. When you solve a problem that has been solved before, obviously you can use that. But if you're solving a problem that no one has solved before, that approach is probably not going to work for you. And you do have to go a little bit into that selection, a little bit of that training. That doesn't mean that you have to be like a mathematician and a statistician and a machine learning expert and an app developer expert and a sensor specialist to understand your input data. Although if you are all that, it does actually help, but you don't have to be. But the one thing I would like you to kind of take away is that even if you maybe not know all the detail, have some kind of intuitive gut feel on how the algorithm you have chosen and how the data that has been trained with is working so that you kind of know when things are going wrong where you may be starting to fix them. And I kind of want to show you what I mean by this gut feel. So let's look at selection. So these are literally, like I told you, it's hundreds of algorithms. These are just a few of them. They're sorted by how they work. So how would you go about even like knowing where to start here? So let me give you an example of one of the most simplest one called linear regression. What linear regression does essentially is when you're on the x-axis at the bottom, it essentially predicts you what the y outcome of that x-axis is. So think something like, if you had like square meterage of your flat at the bottom, what could be your house price for that flat? And it makes the assumption that this relation is linearly connected. So it makes the assumption that as your square footage grows, your house price also grows linearly to that. So now, if you think about the example I was showing you at the beginning, and you kind of look at this image with the colors, and I'll ask you like, call out the colors that are in this picture, do you think that linear regression may be able to solve this problem? I see a no. It's a good no. This room knows a lot, actually. Yeah, it's a no. It can't solve it, right? It's a prediction algorithm that has a linear relationship. We want to have the color out. It's not the right algorithm to do that. So without having to understand any of the maths of linear regression, you kind of already know, maybe not my algorithm. So let's look at another one. So another one is called logistic regression. And in logistic regression, you essentially try to say, like, I'm trying to create discrete boundaries between different kind of my samples. And I'm kind of like going to call anything at the bottom there this like square. And anything on top there will be x's, and anything on the side will be triangles. And of course, you can have as many classes as you want. And now if I ask you again, like, do you think like that the problem that I showed you with colors, do you think this algorithm may be able to solve it? Yeah. I see some nodding. I hope so. I haven't actually tried it, but I was like thinking like, yeah, this one probably would. So this one is definitely one I would recommend you like, yeah, if you find a logistic regression model, and if it's like multinomial, that's probably one you will be in luck with. So as you've seen, when you're selecting an algorithm, having this like intuitive kind of understanding without the details of the math really can help you to actually pick something that's going to be successful at solving it. Now let's look at training. So again, that's a complex thing as well. Training an algorithm is like, remember, all these algorithms start out being very generic. And so the training is the bit that makes them specific to your business problem. So unless an algorithm has been trained to your specific problem that you're trying to solve it, even if it's the right algorithm, it's not going to give you the right answer. So these two have to kind of both be together. Now, there is 3 ways you can train an algorithm. The first way is you do supervised learning. The second one is you do unsupervised learning. And the third is a combination of the both. The supervised one is essentially when you feed an algorithm with input data that you already know what the right outcome is. And so the algorithm takes that income and it knows what it's supposed to have as an outcome. And so that's the way it adjusts its internal model essentially to do just that. But in many cases, you may not have a data set where you know what the right outcome is. And you're still not lost. You could look at unsupervised learning algorithms. Generally, they go hand in hand. So generally, like, there is a few algorithms that can do both learning and like supervised learning and unsupervised learning. But generally, like, algorithms kind of like are built to one or the other, and they come with models that do one or the other. So now let's look what this actually means. So you already know two algorithms. You know linear regression and you know logistic regression. On linear regression, when you train it, if you think like these red dots on the side that I said like was the house price, this was essentially your input data. So you fed that algorithm with input data where you knew what the square meterage was and you knew what the price was. And all the algorithm did is like, okay, from now on, when you're gonna give me some square meterage, I'm just gonna predict what your square footage is, and I predict it by giving you that line on the blue line, a dot on the blue line. So you can see it's never going to be quite right. So that algorithm is never going to give you quite the right solution, but it's going to be not a bad prediction. That's, by the way, another thing to know. A machine learning solution is never as good as an exact solution. So if your problem has an exact solution, use the exact solution. And machine learning solution can be as best as good as your exact one. But if you already know the exact one, don't bother with this. It's going to be a waste of your time. On the logistic regression, the algorithm does something very similar. It tries to find the boundary lines between these different sample sets that you've given it. And then from then away, you can just give it a sample and it will tell you in which of this part it will fall in and just call it out like that. So now, when you're training an algorithm, essentially it's quite easy to either not show it enough training data or to show it too much. So the training data that you show, it really, really matters. If you don't show that algorithm enough training data, it will essentially have a quality that's called biased. So it essentially will say, and that's that orange line that you see. So it just didn't bother kind of quite mapping it. And it's just gonna go like, oh, I just see two things. It's one of those or one of these. And I'm kind of like quite inexact. So you see like any of the blue dots on the bottom of that orange line, that would have been misclassified if you were to feed them in. Now, if you, on the other hand, give it so much training data and so much kind of like different exact training data, for example, in our color picture, if I would give it like hundreds of different colors of blue, it's going to attempt to classify these hundreds of different colors of blue. So I'm not going to get that outcome that I want, that I essentially say like, hey, any kind of shade of blue looking like color, please call it blue. That is called overfitted. So it essentially lost its ability to generalize. It looks like an exact solution for that data set, but it essentially can no longer generalize. So that's also not what you want. So the sweet spot is essentially that black line in the middle, where you separate these two data quite well, but where you will have some misclassification, but your algorithm is now actually able to run data it hasn't seen before. Now, if you think back to the example that I gave at the beginning with the picture, with the image that you've seen, and you think about what sort of data would you train that model with? I was kind of thinking my thing, I probably actually wouldn't show it the same image. I probably would present it with the kind of color I wanted to be able to classify. And I would essentially just give it a picture of that exact color to essentially make it classify into these colors. And from then away, I would feed it images of that picture, and I would have quite high hope that it's going to call out some of the colors that I have specified, and that it will somehow have put its boundary in the middle, that when these dots run in the middle, that they'll be blue. And that even something that looks like white, if your maturity thing is blue, it will still be called blue. So now, again, so a summary on training, like the way you've trained your algorithm, the training data you use to train your algorithm incredibly matters. And again, having an intuitive understanding on how your algorithm works, how it's optimizing itself, helps you, because otherwise it's very difficult to kind of know what sort of training data to feed it and maybe what goes wrong. So now we've kind of approached the last step of a machine learning solution, which is the execution bit. So this whole training and this whole selection of algorithm was actually done using statistical model. Like the sort of languages or the sort of frameworks and the sort of tools you want to use are tools that are very good at running mathematical formulas, that may be able to plot these mathematical results for you, where you can try out things, change it, do some error calculation, that sort of tools you will have been using to create that trained model. But what you actually want to do, and probably what we all want to do on our phone, is to actually have that algorithm, now that we have this cool algorithm, and run it on our phone. So essentially, that's the execution bit. So you think I had this image, wouldn't it be great if I can just have my phone pointed at any sort of object, and it would call out, that's the input data, is essentially that picture of the thing, and it'll just call out to me hey, some labels in that picture, there's blue, white, and silver. Now, to do that, essentially, without Core ML, you'd essentially have to sit away and translate whatever your training data is into Swift, and you'll have to figure out how to performance optimize it, and you'll have to figure out what the best way is of make this run effectively. But what essentially Core ML has done for you is that I'm going to start on the other side. So you essentially have your trained model. As I said, your trained model, you probably used a tool out there that's your favorite tool for creating machine learning solution. Then Apple has provided you with the open source Python tool Core ML tools. And that open source Python package allows you to translate the trained model into a file format, which is called ML model file. And that file format then can be understood by Xcode. And when you essentially you use this Python tool to create one of these files out of your trained model. You pull it into Xcode, and Xcode from then away is essentially able to handle your machine learning algorithm as if it were a Swift framework. So from then away, essentially all you have to do is to call your model and essentially say, like, my model, it will even know, like, it's even typed, the input is typed and the output of it is typed as well. So in my case, where the input is a picture, it will know I'm expecting a picture, and it will know, oh, your output is like strings. So it will essentially be typed knowing what your input is expected and what your output is, and you kind of had to write no code. It also will guarantee you that it uses the best performance for your model essentially on that phone, on that device that you're running it with. There is also already in Swift a few other libraries that are very domain specific. So there is Vision, which is a framework that does machine learned implementation of, for example, face detection or object tracking. So if you're trying to solve any of those problems, you don't have to do your own model and you don't have to train it yourself. You essentially use those frameworks. The same for natural language processing. So if you do anything of problems like language identification or named entity recognition, use those frameworks that are already in Swift. You don't have to go back and create a trained model yourself. If you have a trained model, or if someone else has written a trained model, you can also go on Apple's webpage, and there are trained models already available. However, the one thing you have to know, they've been trained to solve a specific business problem. So if what you want to do is the same, they will work. If what you want to do is something different, they're not going to work for you. And so essentially, like, I may also, like, I want to make some benefit of having, like, blue-shirted people in the room. So one thing that Ayuda, that we really would love to kind of extend on Core ML is, like, first of all, that obviously the more of these trained models are available to us, I think the more it's going to help us developer use it. It'd also be useful for us to essentially have videos of this model. So as I said, like, having this intuitive understanding on how this model works, like, one easy way to know how it works is if you just have a video and see it run. And see it run on, like, what does it classify right, what does it not classify, and we could just watch it back and go, like, yep, that looks like what I tried to solve. Another thing, of course, is as well, and one thing that we're hoping, especially at Ayuda, about is we have, like, the Vision framework here, and we have NLP. We would love to have more of this, like, generic problem. For example, one I can think of is, like, automated workout detection. Our users don't want to say, I'm starting a workout and I'm ending a workout. So either Ayuda now goes away and implements the machine learning model for doing that automated, or maybe Apple creates that because, you know, I mean, it's already on the Apple Watch and it'd be kind of handy. So to summarize the execution bit, like, the execution bit is literally just where you translate what you did in, like, a more mathematical, like, statistical, whatever that word is, way, and translate that into Core ML so that you can call it from your Swift code as if it were just any other kind of class that just did some algorithmic outcome for you. And that's me for tonight. Thank you very much. Any questions?